Here's another little few examples of separable differential equations I thought that may come in handy for some of you, because the first video I put together had, I think, some of the more straightforward examples, and I wanted to show you what to do when things get a little bit more hairy. The one thing you do need to remember that I didn't stress in the first lesson is that when you're doing your separation, it must be finalized. I'll just underline the word must, but it must be finalized with multiplication or division. You cannot separate with addition or subtraction. Now that doesn't mean that addition or subtraction can't be used in the early steps, but in the very end, when you finally separate your variables, it has to be done with multiplication and division. And ideally, before you separate, you want your differential equation to look like one of these two. You either want dy dx equals a function of x over a function of y, or dy dx equals a function of x times a function of y, because in both of these cases, in order for me to move for this first one, in order for me to move my y over, I multiply, which is one of the desired operations, and to move my dx over, I will multiply by dx. This one, to move my dx over, I would multiply by dx, and to move my g of y over, we would divide by g of y. So you want to get it in one of these two generic forms, and then you will use multiplication or division to finalize the separation. So here are a couple of examples, and this one right off the bat, notice that this is xy plus y. It's not a function of x times what in the world? Go away. It is not a function of x times a function of y, or a function of x over a function of y. So we're going to have to do a little bit of work to this to see if it can be separated. And what I notice on this one is that I can actually factor a y out of the right side of the equation. So if I take a y out, that will be y times x plus 1 equals dy dx, and now I do have a function of y times a function of x, and to finish separating this, I would multiply both sides by dx, multiply by dx. So if I do that, the dx's cancel, and then at the same time, I'm going to divide both sides by y. And if I divide both sides by y, then my y cancels right here. So I did multiplication and division in order to separate the variables, and I'm left with dy over y is equal to x plus 1 times dx, and now we're ready to integrate this differential equation. Left side is going to be the natural log of y. The right side is x squared over 2 plus x plus c, and then when you solve that for y, it's e to all of that stuff. So e to the ln y is y. E to all that stuff, I bring that c all the way down front and I change it to an a. E to the x squared over 2 plus x. And there is your solution to the differential equation. Now I didn't give you an initial condition, so we can't solve for a, but that is how we would separate and solve this one. Alright, let's try this one. 3x plus y times y prime equals 2. Let's see, I'm not a big fan of the y prime notation, so right off the bat, I'm going to get rid of y prime and change it to dy dx. And I'll just bring all the rest of the stuff down. 3x plus y equals 2. And then I see the 3x plus y. I really want my 3x on the other side of the equation. So I'm actually going to subtract the 3x. Now, I know you're probably thinking, but you said everything has to be done by multiplication and division. I meant like the very final step. Once you finally break apart the dy dx, that's when you need to be multiplying and dividing. But here, I'm okay to subtract my 3x over, so I'll have y dy dx is equal to 2 minus 3x. And now I do have a function of x over here by itself. It's all of 2 minus 3x. And what I'll do is, I've already got my y's on the left side. I need to move that dx over. So I'm going to multiply. Now that I'm separating the dy dx, I'm going to multiply by dx. My dx's cancel over here, leaving me with y dy equals, and then over here, it's all of 2 minus 3x dx. And that is good separation. I have y times dy and something times dx, and now we can integrate this. So anti-differentiate, integrate it. Left side is y squared over 2. Right side is 2x minus 3x squared over 2, all plus c. And if possible, I like to solve for y, so I'm going to multiply the entire equation by 2. And when I do that, I get y squared is equal to 4x minus 2 times 3 halves is 3x squared. And if you double some random number, it's still some random number. You can put 2c if you like, but it's not necessary. Then I'll take the square root, and what you need to remember is when you take the square root to solve an equation, this is what everybody always forgets, is there is a plus or minus in front. So it's plus or minus, and don't forget that that plus c is under the radical. You take the square root of everything right here, so the c does go underneath the square root. So there's that problem, number 2. Okay, let's try this one. dy dx equals x squared plus y squared. And this one, again, I've got that addition right there. If it was x squared times y squared, this would be wonderful, and I could separate it. But what I've got here is x squared plus y squared. And there's not much you can do with this. You can't factor it. X squared plus y squared won't factor. Like that very first problem, we were able to factor out a y. I can't do that here. I suppose I could subtract the y squared, but the problem is if I subtract the y squared from both sides, then I've got dy dx minus a y squared equals x squared. And when you're doing when you want to separate, when you get ready to integrate, it has to be a function of y times dy and a function of x times dx. If I tried to multiply by dx right now, yeah, I could multiply by dx, and that would give me x squared dx on the right side. But the problem is on the left side, since that's 2 different terms, I have to distribute that dx, and that would actually give me dy minus y squared dx, and it's not helping any. You're not going to be able to get a true separation of the variables, no matter how much algebra you try to play with this. There will always be a dx or an extra dy or something kind of polluting this problem. So at this point, we would say that, you know what, this is not separable. You cannot separate these variables. Not separable. Therefore, we're not going to find the solution. There may be some higher level of calculus that allows you to find the solution to this differential equation, but in AP Calculus, we only deal with separable equations, so therefore, we won't find the solution. We won't find the solution because this thing, that's a cool looking f, because we cannot separate the variables. The separation must be done with addition and with multiplication and division, and you have to remember, when you multiply, you have to follow the properties of multiplication. If you multiply one thing, you have to multiply everything by dx, and that's really what messed up number 3 here. Alright, last one. X dy dx equals y ln x. And let's see, this one, it's all multiplication. There is no addition sign here, so I'm thinking that we could separate this. This has got stuff all over the place. I may do this in a few different steps. I'm going to move the y over. So I'm going to divide by y. I'm going to divide by y. And that will move the y over. And at the same time, I'm going to divide by x. And that would move this x over. And that would give me dy dx all over y is equal to ln of x over x. And I still need to move that dx over, so let's multiply both sides by dx. And when I do that, the dx's cancel, leaving me with dy over y is equal to the ln of x over x dx. And I do have separation there. I've got all my y's on one side, all my x's on the other. It was all done by multiplication or division, and we are ready to integrate. Left side's easy. 1 over y dy, or dy over y, integrates to the natural log of y, equals, now this one's a little bit tricky. I'm going to have to come over here into Thoughtland to finish this one up, because what we have here is one of those tougher integrals. And when I say tougher, I mean it's not power rule or something you easily recognize. The ln of x over x. Now this is a nice problem. It's actually u substitution, and you're going to let u equal the natural log of x. The reason I like that to be my u is because the derivative of ln x is 1 over x dx, and that's exactly what I have here. I could rewrite this function as the natural log of x times 1 over x. And here is my du ready to be used. Yeah. So there's my du. And u, ln x, that's my u. So this is simply the antiderivative of u du, which is u squared over 2. And then u is ln x. So the final antiderivative is the natural log of x squared all over 2 plus some constant. And that's what I'm going to put for my answer right here. So when I integrate this side, it ended up being the natural log of x all squared all over 2 plus some constant. A little bit tricky there, some u substitution. And then we'll finish by exponentiating both sides, making both sides exponents on e. E to the ln of y is y. E to the ln of stuff plus c. I'm going to bring that c down and make it a big constant, e. And this one, there are some properties of logs and exponential functions that you think you can use, but we actually aren't going to be able to do a whole lot to this because it's all of ln of x squared. It's not, the exponent is not just on the x, it's on the natural log as well, which eliminates any possibility of properties that we could use to make this really sexy. So, there we go. There's that one solved and cleaned up, and there are a few more difficult examples of separable differential equations, and hopefully this will help you understand it just a little bit more.